In this video, we're just going to go through some more word problems. We'll also get this idea of average cost coming through. And with that, let's go ahead and get started. So in this first example, we have the manager of a garden store wants to build a 600 square foot rectangular enclosure. So what we have there is an area. And I'm just going to go ahead and draw a picture of a rectangle with 600 square feet as the area. On the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built with redwood fencing. I'm just going to kind of highlight 3 sides with a red pen to show redwood. At a cost of $7 per running foot. So we have a cost per foot there for the redwood sides. And then the 4th side will be built with cement blocks, which has a cost of $14 per running foot. Find the dimensions of the least costly enclosure. So what we want to do here is we want to minimize cost. So what that tells me is we're going to end up having a function for cost, and that's what we're going to want to evaluate the derivative of. Okay, so 2 things at work here. We have area, which comes from width times length, or length times width. We also have the idea of perimeter here, but specifically cost of perimeter. So let's go ahead and label, we have 2 sides that are the width and 2 sides that are the length. In this, it doesn't matter which one's which here. So with that, if I make a function for cost, let's just say C is equal to, so each red side is going to be costing $7. So what I'm going to have is, with how I happen to draw it, is 7 times W plus 7 times L plus 7 times W. And then we're going to add on 14 per foot for one of the sides. So I'm missing a length, so that'll be 14 times length. Now I'm just going to simplify that, so that'll be 14W plus 21L. Okay, so I have my cost equation. However, I have 2 variables, so this is where I want area to come in to kind of help me simplify in terms of 1 variable. So the area is equal to 600, so 600 is equal to width times length. And then from there, I can solve for width, I could solve for length, doesn't matter, I just need to solve for one of the variables. Let's solve for W. So W is going to be equal to 600 divided by L. So what I'm going to do is substitute into W in the cost equation. So C is equal to 14 times, instead of W, I'll have 600 over L plus 21L. So C is equal to 14 times 600 should be 8,400. And then that L in the denominator, I'm going to move it up with a negative exponent. So I'm going to write that as L to the negative 1 plus 21L. And that's just because I know I'm going to be taking the derivative. It's nice to use the power rule there. Okay, so first derivative of C is going to be negative 8,400 and then L to the negative 2 plus 21. Set that equal to 0, so we have 0 equals negative 8,400, and now that I'm solving, I'm going to switch that negative exponent to be in the denominator, so L squared in the denominator, so I get my positive exponent, because that makes solving easier. And then we just keep solving. So we have 8,400 over L squared equals 21. I'm going to multiply both sides by L squared. Divide by 21, which should be 400. Take the square root of both sides. And typically that gives us a plus or minus, but since we're working with a word problem, we'll just be working with the positive value, which would be 20. So we get is the length is 20, which means the width is going to be 600 divided by 20, which is 30. So now is the point where I go back and make sure I'm answering the question. So find the dimensions of the least costly enclosure. So the enclosure should be 20 feet by 30 feet to minimize cost. But it's always a good idea when you get to the end to make sure you're answering that question, because maybe they're asking for what the cost is. So with that, we would need to go back to our cost equation that we started with. But they just wanted the dimensions, so that's all we needed. Okay, a concert promoter has found that if she sells tickets for $50 each, she can sell 1,200 tickets. So we have this relationship of a price of 50 going with a quantity of 1,200. Okay. But for each $5 she raises the price, 50 less people attend. Now that wording there of describing how price and quantity change simultaneously, that gets me thinking slope. That kind of relationship of how quantity changes with respect to price or price with respect to quantity. That's the idea of our rate of change, which is our slope. So what price should she sell the tickets at to maximize her revenue? So we want to get to maximizing revenue, which again would be taking our price function times quantity. So what I'm going to need is a function for price. So what I have right now is, in terms of price, basically a coordinate. In fact, maybe I'll switch to using P and Q, where Q represents quantity. So I'm going to go for revenue. R of Q is equal to P of Q times Q. We have Q would be input, P would be output. So in terms of a coordinate, we have this input of 1,200 gives us an output of 50. Then in terms of slope, what we would have is change in output, which would be our change in price, over change in input, which would be change in quantity. So for slope, what that sentence is telling me, so for each $5 she raises, so that's an increase in price by $5. So in the numerator of the slope, that would be a positive 5 to show an increase by 5. 50 less people attend, so quantity goes down by 50. So in the denominator, I'm going to have a negative 50. So the slope is a negative 0.1. So in terms of our price function, what we have going, so P of Q is equal to, so we have a negative 0.1 times Q, but we don't know our y-intercept, so I'm just going to put a plus B. But what we do have is a scenario with P and Q with the 1,200 for Q and 50 for P. So what I'm going to do is plug that in. So a price of 50 equals negative 0.1 times 1,200 plus B. And then we would just solve for B, which is going to be 170. So our price function, P of Q, is going to be equal to negative 0.1 Q plus 170, which means our revenue function, R of Q, is going to equal taking that function and just multiplying Q through. So it would be a negative 0.1 Q squared plus 170 Q. Okay, so we have our revenue function, and now we want to maximize it. So what I'm going to do, and again, I'm just going to keep mentioning this because we do want to make sure we are in fact finding a maximum. So revenue is quadratic with that Q squared. The value in front of it's negative. So this is going to be a parabola that's opening downwards, which means we are in fact getting a maximum value. Okay, so with that, let's go ahead and take the derivative, which is a negative 0.2 Q plus 170. Set that equal to 0 and solve. So 0.2 Q equals 170. So Q is going to be equal to 850. So we found the quantity of tickets to sell in order to maximize revenue, but our question is, what price should she sell the tickets at to maximize revenue? So we found the quantity. For price, we're going to go back to our price function, so P of, and we want to plug in 850. So I'm going to take negative 0.1 times 850 plus 170, which is going to be 85. So the price should be $85 per ticket to maximize revenue. Okay, 2 more examples here. So we have a company sells Q ribbon winders per year at P dollars per ribbon winder. The demand function is given by P equals 300 minus 0.02 Q. So we have this equation. So it's the demand function, but it's also calculating price based on quantity. So we have that relationship there. The ribbon winders cost $30 a piece to manufacture, plus there are fixed costs of $9,000 per year. So for cost, what we're going to have is $30 a piece, so 30 times Q, and then a fixed cost of $9,000 per year, so then we'll just have plus $9,000 for that initial cost that we'll have. So find the quantity where profit is maximized. Okay, so profit is coming from revenue minus cost. So revenue, we just talked about, is taking the price function times Q. So we have price is equal to 300 minus 0.02 Q. So that means revenue is going to be taking that times Q. So we'd have 300 Q minus 0.02 Q squared. So for profit, what we'll have is taking R of Q, which is the 300 Q minus 0.02 Q squared. And then we're going to subtract the cost function, and I'm going to throw that into parentheses, 30Q plus 9,000. But that negative is going to distribute, so we'll have 300Q minus 0.02 Q squared minus 30Q minus 9,000, which will finally simplify to, let's see, I'm going to rearrange a little bit to negative 0.02 Q squared plus 270Q minus 9,000. Okay, so we have our profit function, and that's what we want to maximize. So I'm going to take the derivative and set it equal to 0. So that'll be negative 0.04Q plus 270. Set that equal to 0. So we'll have 0.04Q equals 270. Divide both sides by 0.04, and that's going to give us Q equals 6,750. So we want to find the quantity where profit is maximized, so that would be 6,750 ribbon winders. Okay, last one here. So we have the cost in dollars to produce Q gift baskets is given by C of Q equals 160 plus 2Q plus 0.1 Q squared. Find the quantity where the average cost is minimum. Okay, average cost. So if we want the function for average cost, what we're going to do is take that cost function and divide by quantity. So we're taking that 160 plus 2Q plus 0.1 Q squared and dividing all of that by Q. So our average cost function is going to be 160 over Q plus 2 plus 0.1 Q. And we want to minimize that, so what we're going to do is evaluate critical values for it. So with that, I'm going to just rearrange this a little bit. So AC of Q, average cost of Q, is 160 Q to the negative 1 plus 2 plus 0.1 Q. So taking the derivative, we will have negative 160 q to the negative 2 plus 0.1. Set that equal to 0. I'm going to do negative 160 over q squared plus 0.1. So 160 over q squared is equal to 0.1. So 160 is equal to 0.1 q squared. So q squared is going to be equal to 1600. So when we take the square root of both sides, we're getting q equals 40. So we wanted to find the quantity, so it would be 40 gift baskets. Now with this one, it's a little more difficult to know that in fact we are finding the minimum value here, because this is kind of, this is a mixture of a function. It's a little rational, it's a little linear, it's a mixture, and I can't quite visualize it off the top of my head with this structure. So what we could do is, if we wanted to make sure that this is in fact a minimum, which means we should have something that is concave up, what we could do is evaluate the second derivative. So we could do a quick second derivative test here. So our first derivative was the negative 160 q to the negative 2 plus 0.1. So the second derivative would be a 320 over q cubed. And with that, what we could do is evaluate that second derivative at 40. So that would be 320 over 40 cubed. And really all I want to see there is we are getting a positive value out. So that means we're concave up when q is equal to 40, which is exactly what we should be having. So that all confirms that we do in fact get a minimum out. So if we can't visualize it based on the type of function, you can always take the second derivative and plug in that minimum or maximum value you're finding and evaluate that second derivative.